Hi, I'm Josh Jordan from the University of California, Irvine, and this is part 2 of my talk on non-Kähler Calabi-Yau geometry and Pluriclosed flow. This is joint work with Mario Garcia-Fernandez and Jeff Streets. So, just in case you didn't see the first talk, there I discussed a lot about background, kind of some basic Hermitian geometry, and a rough introduction to Courant algebroids, and some geometric relationships there. Now I want to talk about slope stability criteria and pluriclosed flow, because that's really where our actual results come in. So the first thing to talk about is slope stability criteria. And I guess even before that, what is slope stability? Well, Donaldson, Uhlenbeck, and Yau were investigating Hermitian-Einstein metrics over Kähler manifolds. And they found this, they were able to relate the existence of Hermitian-Einstein metrics to an algebraic condition called stability of these holomorphic bundles. So we're going to let Mj be a complex manifold with an Epley class A. And then if F is a coherent sheaf over M, we can define its slope, right, mu sub A of F, to be the duality pairing between A and the first Chern class of the determinant bundle of F, divided by the rank of F. I guess I forgot to provide the definition of that little r. It's just the rank of F. And we call a bundle E over M astable if for every subsheaf the slope is strictly smaller. E is called polystable if it's a direct sum of stable bundles having the same slope. So this is an algebraic condition. It's a condition on the cohomology on the Chern class. But it has this immediate relationship to an analytic condition, right? The existence of a metric H on the underlying bundle of F satisfying S sub G sup H is 2 pi times the slope of the identity. And then just to clarify, I guess I didn't give this definition yet, S sub G sup H is the G trace of the H Chern curvature on the holomorphic vector bundle underlying E, right? Donaldson did some work on this for, I believe, algebraic projective manifolds, and Uhlenbeck and Yau did it for Kähler manifolds. This result was then generalized by Li and Yau to compact complex manifolds. Because we don't have Kähler metrics necessarily anymore, the thing we talk about are Godeschamp metrics. Omega tilde is a Godeschamp metric on M, and we take our distinguished Epley class to be the n-1st power of this Godeschamp metric. Then you can relate the existence of Hermitian-Einstein metrics to polystability, right? This is exactly like the Donaldson-Uhlenbeck-Yau result, but it holds for general compact complex manifolds. If you remember, Q tau is just a holomorphic vector bundle. It's a holomorphic vector bundle with extra data. So the theory carries over almost immediately. But at this point you might be asking, well, we have Bismuth Hermitian-Einstein metrics, which are a condition on the first Bismuth curvature, and we have Hermitian-Einstein metrics, which are a condition on the second Chern curvature on some extra bundle, right? Well, these are actually related by Bismuth's identity in the following way. So this second G, capital G, Chern curvature is related to the little Bismuth curvature, right? The Bismuth curvature on the base manifold, this way, right? This is the relationship. So S sub little g sup big G is completely determined by the Bismut-Ricci curvature. You can verify this directly from Bismut's identity. All you have to do is trace it and use this relationship between the Bismut curvature and the minus curvature, which I've mentioned briefly. You can also do it brutally through by-hand calculations. This statement actually implies that G is Hermitian-Einstein if and only if S sub G sup big G vanishes. Okay? And little g and big G are coupled, right? Big G is determined by little g and beta. So in some sense, every Bismut Hermitian-Einstein metric on the base manifold generates a Hermitian-Einstein metric on the underlying vector bundle. Now, this immediately gives a necessary condition for the existence of Bismut Hermitian-Einstein metrics in the following form, right? This is just slope stability. This is just the slope stability condition reinterpreted for Q. And the reason for that is just that Q always admits this G in the upper left-hand corner, G inverse in the lower right-hand corner metric, right? This specific kind of generalized Hermitian metric where beta is 0. And the Ricci curvature, right, a representative of the first Chern class there, it just vanishes. You can compute it out, and it just vanishes. So you end up with vanishing slope for Q, which means that all the subsheaths have to have non-positive slope, and in particular for the Gödel metric. Something interesting to think about, but not super pertinent, is just that this map from omega to the n-1st power of the Gödel metric as an Epley class is typically complicated, right? But when n is 2, Gödel is the same as Pluriclosed, and that map just becomes the identity, which is kind of cool. So we can talk now about our first main theorem, which is the obstruction. It's the obstruction to the existence of Bismut Hermitian-Einstein metrics. So a small piece of definition, we call an n-1, n-1 Epley class positive if it's represented by a Gödel metric in this way. We call an n-1, n-1 Epley class positive if it's represented by a Gödel class in this way. Then we were able to show, using the discussion prior, that on any compact complex manifold which admits a pluriclosed Bismut Hermitian-Einstein metric, if there's a map, nope, I'm all messed up now. We call an n-1, n-1 Epley class positive if it's represented by a Gödel class in this way. Then we were able to show, using the discussion prior, that on any compact complex manifold which admits a pluriclosed Bismut Hermitian-Einstein metric, if there's a map, nope, I'm all messed up now. We call A an n-1, n-1 Epley class positive if it's represented by a Gödel metric in this way. Then, just by the prior discussion, by the theorem I mentioned just a second ago, if MJ admits a Bismut Hermitian-Einstein metric, then there has to be a positive Epley class so that anytime we map M into a complex manifold Z, which is so that the map F is a submersion at least one point, then we have that the pullback of the first Chern class duality paired with our positive Epley class has to be non-negative. And even further, when Z is our original manifold and F is the identity map, we find that this duality product has to be strictly positive unless G is Kähler. Let's actually take a second to prove that. Sorry, I gotta flip through my notes to make sure I don't say anything too silly. There. All right, so we've got our obstruction. We're gonna let G be a Bismut-Hermitian-Einstein metric. Q, a pluriclosed Bismut-Hermitian-Einstein. Q is going to be our holomorphic Courant algebroid, and A is our positive Epley class. Then we know by the prior theory, right, by prior, that Q is A polystable. We also have our map F from M to Z, which is surjective at one point. Sorry, submersive at one point. At least one point, I should say. Then we know that the push forward is going to induce a map from the pullback of the 1-0 forms into the 1-0 forms of M, and the 1-0 forms of M include naturally into Q. But this is good for us, because this means we're almost a subsheaf. We just have to be able to define global sections. To get that, we just have to note that because F is submersive at one point, we can actually apply Sard's theorem. Right, by Sard's theorem, that the set of regular values is dense in Z. So because M is connected and F is holomorphic, we end up with the pre-image of the regular values is dense in M. But this just means that our sections can be extended to all of M, right? Thus, F star wedge 1-0 Z includes in Q as a subsheaf. right? But this is handy for us because we know that by our prior theorem, we have to have that the slope of this guy, which is just the negative pullback of the first Chern class, duality paired with A, has to be negative, and this gives the result. The part about the duality product is strictly positive. Oh, this should be non-positive, huh? The part about the duality pairing being strictly positive with the first Chern class of M, unless the manifold is Kähler, ends up being just kind of a fact of some holomorphic bundle theory that I don't. It's not as enlightening as this part. We can actually go a little bit further and get an even more concrete corollary out of this. If Z has a negative first Chern class, then M cannot admit a pluriclosed Bismut-Hermitian-Einstein metric. Okay, so any manifold that admits a pluriclosed Bismut-Hermitian-Einstein metric can't have a map where at least one point is a submersion into a manifold having negative first Chern class. This basically just ends up being an application of our previous argument and the Obstruction theorem. From here, we can build certain principal torus bundles to show that there are infinitely many manifolds in any complex dimension no smaller than 3, which fail to admit pluriclosed Bismut-Hermitian-Einstein metrics. And this is one of the first results in its direction, in that it doesn't make any symmetry assumptions, anything like that. All right. So, on to pluriclosed flow. So our previous discussion, we spent a lot of time talking about Bismut-Hermitian-Einstein manifolds. And Bismut-Hermitian-Einstein is kind of an elliptic, it's an elliptic condition, right? The first Bismut-Chern curvature vanishes. Well, we can transport this discussion to a more parabolic setting, which is given in pluriclosed flow. So on a complex manifold, a one-parameter family of a Kähler form and a 2-0 form is said to be a solution to pluriclosed flow if these Kähler forms are evolving by minus the 1-1 part of the first Bismuth curvature, and the 2-0 forms are evolving by the 2-0 part, right? By minus the 2-0 part. So we'll discuss the relationship between pluriclosed flow, and there's a way of thinking about it as a Hermitian-Yang-Mills type flow of generalized metrics. And that perspective has proved beneficial in the past. Jeff and I actually do, in 2020, we were able to get a Calabi type estimate by thinking this way. But something we kind of need before we can work out all of the a priori estimates is a Schwarz lemma, right? So I think a lot of us are somewhat familiar with the classical Schwarz lemma, which is given right here. Right, sigma is a section of a certain sheaf, And its Chern Laplacian is some positive square term plus the inner product of the second Chern-Ricci acting on sigma with sigma. In our paper, we specialize this to our setting. So we have two Hermitian holomorphic vector bundles, E and F over Mj and Ni. In our paper, we actually specialize this to our setting. We have two holomorphic Hermitian vector bundles over M and N. We call these E and F. E has Hermitian metric G, and the actual Schwarz lemma is not going to depend on the metric we put on F. So then we let phi be a morphism of these holomorphic vector bundles, which covers little phi, a holomorphic map of manifolds. And we'll denote by phi also a section of this bundle here. The dual bundle of E tensor the pullback bundle of F, which it gets induced by the bundle map. And we find that just given G, little g, a Hermitian metric on M, this section has a Schwarz lemma of its own. Okay, we've got our Chern Laplacian, our inner product with the second Chern-Ricci curvatures, and we have this term that we call A, which is a covariant derivative of phi coming from the standard metric that we put on this bundle, right? So it ends up being G inverse tensor, oh, that's my bad. G tilde is the metric on F. I made a mistake there. But yeah, so this G inverse tensor G tilde. Okay, so the metric on F actually does show up in the formula. I just made a small typo. But that isn't exactly the setting that we need it for, so we specialize just a little bit further. We end up with, in fact, this guy right here. So if E over MJG is a holomorphic vector bundle over a Hermitian manifold, and we have two different metrics on E, then the Schwarz lemma just looks like this. And instead of A, we use this quantity upsilon, because upsilon is more standard for denoting the difference of connections. In particular, the difference of the G and G tilde Chern connections on E. Now, when E is our background holomorphic Courant algebroid, G and G tilde can be taken to be generalized Hermitian metrics. And this will be super important to getting a priori estimates on the size of G. Now, I mentioned this connection between pluriclosed flow and a Hermitian-Yang-Mills type flow. Just like Bismut-Hermitian-Einstein is related to Hermitian-Einstein, pluriclosed flow is just this Yang-Mills kind of flow. All right, this can be done straight in coordinates, which we do in the 2020 paper, and I believe we do in the 2021 paper. No, we do it in the 2020 paper, and the 2021 paper, it's just a formal calculation, so we just carry it over. And then just by computing, we get these guys, which are fundamental to our a priori estimates. Now, something to notice is if you drop out this evolution part, this term, right, this Laplacian acting on the trace G tilde, looks a lot like our Schwarz lemma, right? So you've got minus this Laplacian, minus this norm squared of epsilon, plus this trace G tilde, right, this lowering of SG tilde. Now, if you remember, there's usually another SGG term down here. That just goes into the time derivative. That's all that is. Something important to notice is that this last term is linear in the G tilde curvature. Right? A better way to say that, that's not really right. If the G tilde Chern curvature vanishes, this term vanishes. I'm sorry for this. I'm kind of in the middle of some traveling. But I just wanted to say this video ran a little bit long. And this was really the most natural breakpoint I could find, kind of close to the 30-minute mark. So I'm sorry that's a little bit awkward. But anyway. So I've split this second part into 2 lectures, so that makes for 3 videos. The first one on the background stuff, the second one on a lot of this slope stability, and the third one on some more parabolic type results. Okay, so thank you for sticking around. See ya.